All right. Let's start our class. All right, good morning, everyone. Let's start our class. So starting from this week, we are going to talk about heap. We have done with our stack. By the end of next Tuesday, it's gonna be probably the last time that you touch stack, you know. And after that, the final, we're still gonna have something related to stack, but like starting probably from now to the later on and to the end of the semester, we're gonna mostly focus about on heap. We're done with stack related vulnerability at this point. Okay, so then for heap, I hope that many of you have already watched the video because you may already realize that, you know, heap, the way that it works is very different from stack, right? Like heap, especially for, you know, for this course, we've mostly focused on the ptmalloc, like it's glibc's heap memory like allocator was a heap management tool. And different malloc will have the different way, but now we're mostly looking at glibc at this point. So we need to understand how glibc managed to work to dynamically, you know, allocate memory for you when you need, you know, like something like 8 bytes or 20 bytes, that when you need some amount of chunks. And then that is different from stack because for stack, the memory is there, it's static in the sense that if you assign, say, you know, a buffer with the length of 20 bytes, it's like you have in your function local variable, you have a buff and it has like char 20, means that this buffer is within 20 bytes. You will see that specifically 20 bytes statically assigned and allocated in a stack. It's there, it's always there, it's fixed as long as you call the function, right? As long as you're currently run the function. However, heap is different in the sense that the memory, like the chunk or, you know, the memory that you ask for, the size of the, you know, memory that you ask for, like those having a memory specific for you to do something, operations, that is all dynamic in the sense that you're not going to get a buffer, you know, you're not going to get a chunk unless you do malloc. Basically, you tell glibc that, hey, I need a part of the memory to store maybe a string or something else with a specific size, and then they will allocate that to you. And then later on, you can tell them, hey, I want to free this side, this part. I don't need this chunk anymore. And then they were going to do free for you. And of course, the operating system or glibc wants to do this efficiently. And that's why they have a different kinds of, you know, structures that can help like malloc, which is like allocate a memory, right? Allocate memory, free memory, and then reallocate memory efficiently. So that's the reason why you see Tcache, right? Like this is something that we mentioned during the video. So Tcache is a structure. Actually, it's newly added. It was not there. I think maybe since 2.26 or maybe 2.27, like the glibc's version. That's the time that Tcache starts to be created. It's introduced to the libc. But like this is a new type of data structure that will make the recycling of the memory more efficiently. But unfortunately, for that version, which is 2.27, the Tcache design has a bunch of design flaws, and that's why we can, you know, leverage, like use after free vulnerability to gain some privilege, to gain some superpower, such as arbitrary read, write, and execute. Okay, so if you actually try the later, or so the latest version of glibc, you will not be able to see that issue again. So if you have already run, you know, the challenge that I mentioned during the video, you try to run it by yourself. And if you haven't used the glibc version that I provided through the course website, you may realize that actually that's not going to work at all. Like everything just like seems to execute normally. And this is because glibc has already patched this error. So that even though that the use after free vulnerability, which is on the application level. Like even though that use after free vulnerability still exists, the library, or say the memory management library, that part, they have handled this well enough to tolerate that kind of vulnerability. However, this doesn't mean that Tcache is already totally secure. There's still bugs about that, or there's still potential security flaw for that. But I think this is more of the for the education purpose. I still want to talk to you guys about, use after free vulnerability, or the way that we can leverage for use after free vulnerability. So that's why I'm still using this older version, so that you can understand how a used after free vulnerability can be potentially used, by attackers. So that's why we're, right now we're fixing our current, the libraries version to 2.27. And it's already on the course website. You should be able to download that. And you should be able to use that library by yourself, so that you can run the binary application with the specific libc's version, libc's binary, libc's library. Okay, so we are going to have challenge today, just as what we had before the labs. But before that, I want to ask you guys, please raise your hand if you already watched the video, or you already kind of know how use after free works according to the video. Good. Thank you. Awesome. So many of you have already watched the video. I am very impressed. That's great. So do you have any questions about the video? And by the way, if you haven't watched the video, and also you don't know how heap or Tcache those things works, I highly encourage you guys to watch the video first. And then you may actually come across some difficulties to understand today's lab, which is fine, because the lab will still keep open until next Tuesday. But I highly encourage you to watch that video first, because the way that heap works, this is going to be something you have never touched before, probably. So in order to understand use after free, things like that, you really need to understand how heap works first. Okay. Okay, cool. And questions? Yes. Mm-hmm. Yeah. Mm-hmm. Right. Okay, yeah. So let me just generalize your question a little bit. Okay. So what about this? I am going to walk through, the example, or say walk through the slides that I have in terms of use after free, because that will answer your question, how this chunk being reused again, right? So that you can write, or you can use that already freed chunk with a metadata, with the function's address, right? Okay, so let's start from there. Okay. I think, one second. All right, yeah, I also see question from Zoom asking how to do arbitrary read using Tcache vulnerabilities. I think for both of these two vulnerabilities, you will be able to get the answer if I walk through, this piece, this part of the the Tcache working process. Okay. All right. So first of all, raise your hand if you already heard this word Tcache, that you know this already. Good, awesome, cool. So on a very high level, Tcache is a design that glibc has to use and to reuse a free chunk more efficiently. And the reason why they call it cache, just as what they said, it's a cache, basically. Tcache has cache. And then when I say cache, it means that by the time that a memory chunk was freed, this memory chunk will be put into a specific place that will store those information. They're not going to be just return this chunk back to the memory. Well, I mean, when I say back to memory, back to the memory means that they're not going to just okay, put this chunk back and then see, okay, if there is any also free chunks before or after that so that they can like coalesce, like to merge them together to a bigger chunk. This is not the way that it works. They want to reserve this free chunk. And this is because glibc has this heuristics that, you know, smaller size of chunks will be frequently, like malloc will be frequently allocated or freed or reallocated. So that's why they want to reserve that chunk. So that if someone gonna ask for, you know, say a chunk with size of 20, again, they're gonna just very fastly go look at the Tcache and then return that chunk to him right away, right? So this is the reason why they have this cache design. They just want to make it fast, okay? And then the way that a heap works. So by the time that you ask for, you know, a memory with say size of, I'm gonna come up with some random words like, you know, 21, right? So it's like, I want a chunk with 21 bytes. So the allocator is not going to like return you a chunk with exactly 21 bytes. Sorry, 21 bytes. So they're gonna actually expand it, because for that specific chunk, it will have not only the data that you want to store, but also the metadata, which is going to be used by Tcache. So, and also they want to make sure that the size of the actual allocated chunk is aligned. The size of it is a multiplier of 16. So it can be divided by 16. So that's why if you ask them, say, for 21 bytes, it's going to be likely that you're going to have hex 30 chunk, like the size, the chunk with the size of hex 30. So hex 30 bytes, okay? And also, if you're going to ask them not 21 bytes, but like 22 bytes, probably the chunk that allocated is still hex 30 bytes. Until to some threshold that they were like, oh, it will jump from hex 30 to hex 40. So that's why if you look at Tcache, the size of it is all like can be divided by 16, because by the time that the allocator allocates chunks for you, it's always, you know, a size that can be divided by 16. Does it make sense? Yes, question. Yeah. 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 Hex 20. Yeah, good question. So the question, or let me just make your question a little bit more generalized. So say that I want to allocate, I do malloc, say 21 or 22. How glibc works, how glibc decide the number of bytes, the chunk, right? The chunk size when glibc returns you the allocated address. So the metadata, so there are two pieces. One is the actual data that you store in that memory chunk. And in this case, it will be 21, right? This is the size that you want, right? Let me write this. And that is 21 bytes. Besides that, the chunk must have metadata. This metadata will be used later on to store, like, as you said, like Tcache, they're all like the chunk are all linked, right? So the metadata will be used to store the information for that chain, for the link, right? And also that metadata will store whether or not this chunk is being used or being freed right now. So that metadata is 16 bytes. Okay, so combine these two together. In this case, this will be 37, right? And then glibc will find the next, you know, like can be aligned, like the next number of bytes that is aligned with 16. So which is hex 30. So that's why if you ask for you know, a byte, sorry, ask for a memory with 21 bytes, you will be returned, you will get a chunk with hex 30 bytes. Okay, good. And also, like, even though that you ask for 1 byte, I want a memory with 1 byte, it's gonna return your hex 20. Does it make sense? Because again, 1 byte plus 16 bytes, and then you want to cap that to some, the number that can be divided by 16, and that will be 20 bytes. Make sense? Hex 20. Okay, good. All right, so coming back to the chain, the T cache. So when you ask for a new memory location, so when you call malloc, you'll be returned with a chunk. And then by the time that you do free, the way that the T cache works is that it's gonna recycle this freed chunk by putting this chunk into the cache. And the way that the cache works is that they're gonna have a chain for every for every class of chunks with the same size. So that's why if you look at the T cache entries, which is also called T cache bin, each of the entry or each of the bin represent a chain of chunks with the same size. So that's why you found this entry is for the chunk of size hex 20. And then similarly, that is the chunk of size hex 30, and then until hex 410. So there is a maximum size for T cache. If you ask for a larger chunk, and then if that chunk got freed, that will not be saved in T cache. It will directly go to the so-called small bin, large bin, like those things that we will talk about, like the other types of bins that we will talk about in future classes. But now we only look at T cache bins, and for T cache bins, it only accepts chunks with the size between hex 20 and hex 410. Okay. Okay, cool. So now let's say that we have, already have some freed chunks and they're all connected together. And the way that they connect together is to use the metadata. So that's why we have the 16 bytes there in order to chain all the chunks together. Okay. So for example, here, looking at the right-hand example, let's start with the dark green chunk, right? So this is the dark green chunk. So the first 16 bytes is the metadata, is to represent this chunk. So here, 21, it means that this chunk is of the size of 20 bytes. So 1 is a flag because, as I said, every chunk will be aligned with 16, right? So it's always be 20 or 30, like hex 20, hex 30, so on and so forth. So that the least significant digit is not really important, right? So that's why they can use this least digit to represent a flag, to use it as a flag to denote the availability of this current chunk. So that's why, see here, you see 21. So although it says 21, doesn't mean that the chunk is within 20, it's 21 bytes. It means that this chunk is 20 bytes and 1 is a flag, means that this chunk now is free, is ready to be reused or be recycled. So far, so good? Good? Okay, cool. All right, so I'm gonna continue. Then the next 8 bytes is actually an address. That address represents the next chunk after this chunk. And in this case, the next chunk is 603260, right? And that is this purple chunk. Does it make sense? Good. Okay, cool. And then let's look at the purple chunk. Again, look at the first 8 bytes. It represents the availability. It represents the size of this chunk, which is hex 20. And then the next 8 bytes, again, it should represent the next chunk. However, in this case, there's no next chunk. So the purple chunk is the last chunk in this chain, right? So that's why it has 0, 0, 0, all zeros there. Okay, does it make sense? Good. Okay, so if I am going to kind of draw this diagram according to the right-hand side, this memory representation, then you should be able to get the bin, right, hex 20. And the first chunk would be the green chunk. Right? And then the gray chunk points to the purple chunk, right? Okay. And then back with this bin, it will store this, the address of the address of the gray chunk, which is 3280. And also, by the way, you may realize that hex 603260, that's actually not the start of this entire chunk, right? Because if you look at the purple chunk, it actually starts with 3258, right? So I want you to be a little bit careful about this because this information will be used in the future. Like if you see, this is the purple chunk. The purple chunk start from here, right? And then the address of the start is actually 3258, right? Does that make sense? Good, good. However, when green chunk points to the purple chunk, it doesn't point to the first 8 bytes of the purple chunk. It points to the second 8 bytes of the purple chunk. And the reason for that is just because of efficiency, because the reason why they want to have this link together is only just for, allocator to find the next chunk easily. So think about this. If the allocator wants to just find those chunks all the way down, if this information always goes to the first 8 bytes, then every time that they go to the next chunk, they have to do a dereference, right? And then +8, and then dereference, and then +8, and then dereference, right? Which is gonna take more time. So that's why they don't want to do this. They only want to do dereference. So they only store the value, like the address that points to the next chunk's address. Does it make sense? Yes, question? No, right. The question is, if the chunk is not freed, it's currently being used, will that be shown in the chunk? The answer is no. And the way that it works is that because this chunk are all just free chunk. So if that chunk being used or being reused, you will not be able to see like the metadata information anymore. So, and actually it goes to that question. Now we can talk about how Tcache works when someone's going to malloc. Say right now we have green chunk connected with purple chunk, and they're all at Tcache right now. And then say, let's say someone's going to do malloc. Okay. Say, not 20, like malloc 8. You can put a 9, you can put 10. It's safe, but like for this size, glibc will give a hex 20 byte chunk back, right? So glibc will then look at the Tcache tree and then see if there's any chunk that is reusable. And of course, in this case, it's reusable because we have 2 available chunks, right? And then Tcache will always use the first one. And the reason is just because of efficiency. They can use the second one, or they can use the last one. However, if they use the last one, they have to start from there, go here, you want to find the last one, and that costs time. And then, so they don't want themselves to be bothered with that, and then they always just want to use the first one. Okay. Yeah. So again? Yeah. Right. Yeah. So if you use a green chunk, then that information, which is the purple chunk's address, right? That will be stored to the bin. Okay. Good. So in that case, then, sorry. Yeah, I mean, in that case, then, you will be able to use this chunk first. And then actually this operation is relatively easy. You just like always find the first chunk and then read the purple chunk's address by looking at the metadata of the gray chunk, right? And then copy that address to the bin, the header, and that's it. Good. Okay. So this is the way that a key cache works. And then now we got to the time that we can start to talk about the use after free vulnerability. Sorry for this very long delay. I hope this is not too boring for you. Yeah.
Well, why is it that we are kind of having a leakage of this? Like when we thought malloc, it would only give us one chunk, right?
Yes.
So why is it that gdbc does this kind of linkage with all the chunks?
Yeah. The question is, why does gdbc wants to do this this chunks? It's because they want to have a space that stores those reusable chunks, because they think that those chunks will be frequently used and reused, like they're going to be frequently malloc or free. So they don't want to really like make this chunk goes back. So consider that there is a pool of available memory, and they don't really want to do like every time they're gonna return this 20 bytes and then put it back to the pool. They want to have a middle ground so that we can put those smaller chunk or available chunk to that middle ground so that they can get this very easily. So that's why this is called a cache. It's like, you have computer. Besides, between your actual, between the memory and then between the register, there's a thing called cache, right? So it's a similar merit, just be more efficient. Okay, good. All right, so then let's come back. Let's talk about the actual vulnerability. Okay, use after free. How does it work? What happens with the what happened with the T chunk when use after free vulnerability happened? Okay. All right. Actually, before that, let me just have some water real quick. I got a question here. If heap chunk should be a multiple of 16, why isn't minimum size hex 10? It's because the metadata itself already occupy 16 bytes. So if you ask the allocator for, say even 1 byte, that means that you need to have 1 byte of actual data plus 16 bytes of metadata. And then you will have, you're gonna kind of increase the size to be a multiple of 16. So that's still gonna give you hex 20 as a minimum. Okay. All right. Okay, coming back to the use after free vulnerability. So now you know that if a chunk got freed, it will actually be stored to the T cache. It will be the part of chain, right? So if I already have this chain with the chunk, it means that those chunks are already freed, right? Okay, and then now, and malicious people, or say if there is a vulnerability, then attacker can potentially cause this chunk. So if there's a vulnerability that allows you to access those freed chunk, for example, if you have something like, say P is equal, this doesn't work. Say P is equal malloc, right? And then you free P, right? But then you can still do something like P is equal to some value. Or say you can do star P is equal to, say, hex 1, 2, 3, okay, something like that. So suppose that you can still do some operation of the pointer after you free the pointer. So that means that now you are going to directly operate on those free chunks. And the way that you could do is that, 1 second. Is that someone wants to join? Okay, never mind. So you can change the metadata at that point. So if you already freed for this chunk, it will be freed, but then you can still use this pointer P, use this way to, get the address of this chunk. And then if you do start P, like you dereference the pointer and then write some values there, right? You can change that value to something that is controlled by yourself. So for example, if I am going to change this value to a victim, like to whatever address, then by the time that I do true malloc again, I will be able to get this address back. Does it make sense? Basically, if I am going to change this value, I'm telling the T cache that this chunk is no longer, or say in this case, is the green chunk is no longer, chained with the purple chunk. And then this green chunk is changed by another chunk with an arbitrary address, the address that I can specify. Okay. And then if I am asking, to have 2 more chunks with the size of hex 20, then this chunk will be returned to me, right? And then if I make this place special, then that means that I can read and write this particular address that I specify. Does it make sense? And that means that you can do arbitrary read and write, means that you can arbitrarily read or write any value at any address. And then when I say any address, the address is going to be the victim. Okay, does it make sense? Good, good, okay. And then this means, so what we could do is that let's put this victim address as the address of a GOT table entry, right? This is going to be very similar to what we did when we do, format string and the buffer flow, right? So like you change a function pointer, you change like libc's arbitrary like printf, right? Or libc's malloc, right? The function's pointer, which is stored in the GOT table. So you put the victim, the address, you put the victim, the address of the GOT table, so that by the time that you return, when I say return, means that by the time that you call malloc for 2 times, so for the second time, this victim will be returned to you. So you will be able to get a pointer or get a pointer that points to the GOT table entry, right? And then at that point, you will be able to write a value there. Does it make sense? So it's like, if now you're doing 2 times of malloc, right? And then for the second time, say it is P1, this will be the victim, right? And then you can read by like dereferencing this pointer, or you can write by this is equal to maybe the win function. That means that in this case, you overwrite the GOT tables entry, you overwrite, say, malloc, or you overwrite print glibc's printf with the function of win. So in the future, if you call malloc or if you call printf again, we'll actually look at the GOT tables entry and then call win. Does it make sense? Good. Yes, question. Yes.
The example that you discussed in the video.
Yeah.
In that we did it like for 3 times in the day. So like my question is like, why did you like do 3 times? Why didn't you like just do it like just use 2 chunks? Why did you like go to the 3rd chunk? Like we could in the second time that we are doing malloc, we can directly pass the wins address there, right? Like how?
Are you saying that? Are you asking me? I'm trying to understand your question. Are you asking me that why do we have to do 2 chunks? I have green and purple and then redirect to gray. Can we only do 1 chunk? Is that your question?
Yeah, like after green, then why can't we like?
You can. Yeah. So the answer is yes, you can. You actually, today's lab is the same as the one that I'm showing the video. And for this lab, what you could do is just forget about purple chunk at all, right? So you have only one green chunk. And then you allocate it, you free it, so that it will be in T-hash, right? And then if you look at the metadata, it will, like the second 8 bytes will be just 0, 0, because this is the end of the chunk, right? And then you just overwrite that value using use after free, you will be able to change that to just like, instead of having this, you are setting up a hypothetical chunk which going to connect to this. So the purple chunk is not necessary. Does that make sense? Yeah, good question. All right, question here. Once I get my victim pointer on T-cache, how do I read its value? You don't read you read this value by doing 2 times of malloc so that you will get the pointer and then you dereference the pointer. You can do read, you can do write. Do I need to do something like print buff in order to present? Yes, you do need to do like print buff if you want to read the value. So that means that you have to have a way that you could call printf with the address if you manage to get the victim pointer. Okay. Yeah. So what I really wanted to say is that, you know, I want to guys to have a like kind of a high level mindset, which is that, you know, now we talk a lot of ways that we can do arbitrary read, arbitrary write, and most of the times our final goal is to do arbitrary execution. So actually the spirit of how to transform an arbitrary read or write to arbitrary execution is pretty much the same. Most of the times when we have use after free, when we have a buffer overflow, also when we have format string, is to give you the power that you could do arbitrary read and write. And then you want to convert from arbitrary read and write to arbitrary execution, right? So pretty much like the way that this conversion is pretty much the same. So it's that vulnerability that helps you achieve one of them so that you can just do those conversion all by yourself. So that's why for this vulnerability, all it gives you is just arbitrary read and write, right? And then you're actually using the same knowledge that you had before from the other vulnerabilities that you transform this power. So maybe in your mind, you wanna, in the future, if you're going to do some exploit or if you're going to do some attack, what you want to have in your mind is that, oh, can I achieve arbitrary read primitives? If I can I convert it to arbitrary write? Or if I already have arbitrary write primitive, can I convert this arbitrary write primitive to a more powerful, like arbitrary execute primitives? It's more of like the primitive transformation. Okay, good. All right, so that's pretty much it for today's for today's Q&A before the lab. Okay, so now we can start the lab. It's the same IP address. The port is 51, not 41. I just ran out of digits, so I have to reuse one again. So, but this time is 5 once. The service file already online, the binary is already online, and also the libc is already online. So you want to make sure that you download. It's like the challenge that we had before, the lab that we had before. You need to download both the libraries and the binary file, putting them in the same directory so that you should be able to run this binary by yourself in your own directory, like in your own local space. And in the meanwhile, you can interact with the server and then you can use the source code as a way to understand, to comprehend the program behavior. So I will probably give you, I would say maybe 15 minutes. So now it's 11:12. Hopefully, yeah, I'm gonna shoot for 11:25. We're gonna start to work on this together. So if you can work on this by yourself, that's great. Do it right now. If you can't, if you still don't quite understand how that works, it's totally fine. What you could do instead is that I want you to write a couple of functions that you can interact with the items of the menu. So if you run the program or interact with the service, you will notice that there are a bunch of menu items. You Frida Chang, you Malacus Chang, you list them all, right? So I want you to write an interaction with each items of the of the menu item, so that later on you don't have to worry about how to implement the, say, malloc, right? So that you can only, you will be able to only focus on the attack itself. I don't know if that makes sense to you. Okay, so like, yeah, think about those, implement those actual operations at this point. Question? All right, guys, let's start. How many of you know how to do this work? I mean, how to, solve this challenge? Raise your hand if you know that how to solve this challenge. Good. Good. Awesome. Okay. Now let's work on this together. I hope that you already implemented the interface, or say those functions that you can directly interact with each items. So I'm gonna ignore that part. So for this attack, we're gonna be mostly focusing on how to attack. Okay. So I guess let's do this in this way. So on the left-hand side, I'm gonna run this program and with GDB. Okay. So you will be able to see what's going on if we do, malloc, if we do free, things like that. And then in the meanwhile, we're gonna kind of record what we did on the right-hand side. And then after that, you have that kind of the operation order, you have that recipe, and later on you can use your implemented interface to, to interact with this recipe or kind of to implement the recipe. Okay. All right, so let's try this together. First of all, I suppose that you already know the vulnerability, right? It's pretty straightforward. Basically, you will be able to see the menu, right? And then if you free a pointer, you will still be able to call edit to edit that specific chunk, right? Okay, so let's do this together according to what we said, in terms of the use of the free vulnerability. We need to free, right? And of course, before free, we need to malloc them first. So the first thing that's gonna do is to malloc with some randomize. You can, I'm saying, I'm making it 8, but you can make it, like 2, make it 3. It's gonna be up to you. I'm gonna just use 8. You can do it with arbitrary value as long as the bean size is gonna be, fixed. Okay, you can also use the beans of hex 20. You don't have to use this bean with the size of hex 20. You can use 30, you can use 40. As long as you keep in the same bean, you're all good. Okay. All right. So now let's use malloc with 8. Okay. And let's free the pointer. So that is pointer with index of 0. By the way, I think that there is can you guys see that, like I said, I mean, people from the classroom, can you guys see that clearly, or do you want me to move a little bit? Does it bother you? No? Good. Okay, I'm gonna continue then. Awesome. Okay, so, and on the right-hand side, I'm going to record what I did. Okay. So the first thing that I did is malloc 8, right? And then second thing is I freed the pointer. Okay. All right. So going back to this panel, after I freed, let's take a look at the current bin, what the bins look like. Okay. So you can do bins from pound back. And you found this is the current bin, right? So in the Tcache bin, it has 1 item, right? And that's it. And in fact, if you look at the bin, which is at 603260, right? So use this, you will be able to directly see the heap. It also tells you that this, the purple one, right? This is the Tcache bin. Make sense? All good? Cool. Okay. So let's continue. According to our operation, now we already freed, right? So we need to start to use, because hopefully we want to change the value of here, right? Because this is the place that is going to store the metadata. Is that right? Good. Okay. So how are we going to do with that? We need to allocate, right? We need to kind of like allocate this chunk. So the way that it works is that we need to use the third option, edit, and then the chunk, it's chunk 0, right? And then we want to have some values there, right? So what value do we want to put? So now if we are going to change that, I'm gonna just put a random value there. And then you will be able to see the change, okay? So I am going to, I don't know if they can take hex or take int, I actually forgot, but let's try it. Does it work?
You need to, for like now,
That's right, yeah. I'm gonna do this real quick, because I forgot the format that I can put here for the edit. Okay, so it does take a, but it will take it as a string. Okay. Let me continue. So still, it's here. So we want to put the address, right? As, can I have your name, by the way? Is your name? Lucas? Yes, as Lucas said, we need to put the entry, right? The God table's address, right? Okay. So the third thing is to add it with the, and then it should be the God table address of, say malloc. I'm gonna just use malloc in this case, okay? But then we need to figure out where that is, okay? I mean, if you're using the Pong tool, you can just easily do that from, Pong tool's interaction. But now what I'm going to do is actually I can do this. I can go back to the GDB and do clock that. It will be able to give it to me. Where is it? Malloc is here. Right, so this is what I want to give them, right? But because it takes the byte, right? So I cannot just type this value to that directly, because it will take each of the character there, right? So that means that in order to do that, I need to, when I send this, I need to have something like, E0, and then it is the formatted God entry, right? So that's gonna be this. Right? And then in that case, then you will be able to, make this current value, this value, right, with some address. And then now just for ease of representation, because I don't want to implement here and I show you right now, I'm going to just like do a hack. It's not going to work every time that you try it. I mean, it's not going to work if you run the script, but now just like, since I'm interacting with the process directly, I'm going to just use set to directly set the address value there. Okay. So I am going to set this value equal to malloc's address, which is this. Okay. Did I make some typo? Let me check that real quick. I think this value is not the value that I set, right? Oh, it's because I know. I probably need to do this. Okay, I need to remove that 6-1, which is the A that I put there before. Okay. No worries. I can do that. Which is, I think it's that, or maybe it's 4. Let's take a look. Now it's good. Right, okay, cool. So now we change this value to be equal to the God table's entry, right? So that means that if we are going to malloc now, let's continue. And we're going to do malloc. And then let's take a look at the bins after first time of the malloc. So you see that the original, the first chunk is already being, reused. And then now the beans has only the second one, which is the God table's entry, right? Okay, let me continue. And also let me write this down. So the next step is to do malloc again, right? And then the fifth step is to malloc again. Okay, so we are going to malloc and then 8 again. You can do 2 actually, it's the same, but I just want to be a little bit more consistent. Okay, and then let's take a look at the bins. The bins are all empties. And then if you look at the continue. Let's look at the pointers that I already have, right? So the third pointer is the pointers that we have that is supposed to be malloc, the GOT table entries, right? Okay, and then the next is that we can then overwrite, like write some values there. Let's take a look at this entries first. Now, by I am going to actually, let me start to add something. So I'm gonna do added, and then the pointer, which is index of 2, and then put some AAA there, okay? Okay, and now if I am going to take a look at GOT tables entry, which is, where is malloc? Here, right? And then you see that the current malloc's entry becomes to be hex A, like 616161, and that's AAAA, right? And of course, what you want to put is to change this to function win, right? Okay, good. So then it means that after we do a second time of malloc, what you want to do is to add it with that pointer of index number 2 with the symbol of win. Okay, all right. So let's take a look at the win function. Actually, let's see if I can get the win function's address. Okay, it's this address. And I am going to make the entry is equal to this, right? Okay, and then let's take a look at malloc again. Okay, so this should be the value that after we, do the added. And then now if we let the program continue, all we need to do is just call malloc so that it will redirect it to win, right? So we can just do malloc with some random line. Doesn't really matter what it is. As long as it start to call malloc, we're all good, right? I can do malloc 1. Okay, and now we are at the win function, right? And it will start to ask you answer right, and you can record yourself. Good. Okay, so the next step will be malloc with some random bytes. Make sense? Good? Awesome. Okay, so that's pretty much for today's lab. I hope that you can do this by yourself, because I think that this is easier than for mastering. I hope you do think so. Okay. Cool. All right. Yeah, that's it. Thank you, guys. See you next week. Yeah, just give me 1 second. Okay, is that about the today's class, or is it about assignment? As actually, if it is about assignment, do you mind me call the girl over there first, because she want to talk to me? Yeah.